Gold remains a highly valued metal today, generating nearly 200 billion USD in revenue annually. The initial step is to locate areas likely to have gold. Geologists and mining firms perform thorough surveys, prospecting, and geological assessments to identify promising gold-rich zones. This often involves studying geological maps, taking soil samples, and utilizing sophisticated techniques such as remote sensing and geophysical surveys. Once a likely gold deposit is found, the area is readied for mining. This includes clearing away vegetation, building access roads, and setting up necessary infrastructure like camps and other facilities. Once preparations are complete, mining for gold begins. Most gold is sourced from lode deposits, also known as vein deposits, where gold and other metals are concentrated in rock crevices. Extracting this gold involves hard rock mining, which means drilling and blasting to remove the gold-laden rock, or ore. Miners venture deep underground, over half a kilometer down, bringing with them specialized machinery tailored for the drilling. This machinery includes a long-hole drill rig, typically outfitted with a drill steel, a long hollow tube, a drilling machine, and a source of compressed air. Positioned underground at the chosen spot, the drill steel is thrust into the rock or ore. The drilling machine then starts spinning and simultaneously pushes the drill steel deeper into the rock. Compressed air is pumped through the drill steel center, helping to eject the rock debris from the borehole. The design of the drill holes follows a specific mining blueprint tailored to the deposit's characteristics. These plans are crafted by the mining company's geologists and experts. They meticulously determine the size, spacing, and angles of the holes to maximize rock breakage while ensuring the safety and efficiency of the blasting operation. Once drilling concludes, the next step is prepping the holes for explosives. This involves clearing out any debris and fitting various elements such as stemming material, which helps control the explosive force, along with detonators and initiators. After these preparations are complete, the explosives are carefully inserted into the holes, and the blast is set off from a safe distance. The explosion effectively shatters the rock or ore into manageable pieces that can be easily transported and processed further. Following the blast, miners employ a mucking machine to move the ore to cars destined for the main shaft, and subsequently to the surface mill. Utilizing mucking machines streamlines the mining process by automating the removal of loose material, which would otherwise need manual labor or other machinery like loaders or trucks. Initially, the gold-containing material, such as ore or scrap, is crushed and ground into small gravel-sized particles. A mill then further grinds this gravel into the fine texture of beach sand, increasing the surface area to enhance subsequent chemical reactions. The factory introduces a mix of water and cyanide to the finely ground ore, creating a slurry. This mixture is then ground again in another mill into a mud-like pulp, which flows into large settling tanks. Here, the heavier wet solids sink to the bottom while the lighter water drains off. Workers move these dense solids into an agitation tank and inject air into them. This step, known as aeration or air agitation, introduces oxygen into the mix. The oxygen triggers a chemical reaction with the cyanide and the gold in the ore, causing the gold to dissolve into the surrounding water, forming a gold-cyanide complex. After this reaction, the slurry passes through drum filters, which are large rotating cylindrical filters with a porous surface that separates the liquid from the solids. The resulting solution contains the dissolved gold, which is then isolated through a chemical process called precipitation. Common agents for this include zinc, carbon, or aluminum, which react with the gold ions to form solid gold particles. These particles are then filtered out, still carrying some impurities. To further purify the gold, it undergoes smelting. During smelting, the solid gold, now called gold concentrate, is mixed with flux materials such as manganese dioxide, chloride, silica flour, borax, and sodium nitrate. These flux materials help by lowering the melting point of impurities and facilitating the separation of gold from other elements in the concentrate. The gold concentrate mixed with flux is placed into a furnace, a high-temperature chamber designed for such tasks. Within the furnace, the mixture reaches temperatures around 1600 degrees C, melting it down. The furnace rotates to ensure the mixture heats evenly. At these extreme temperatures, gold is separated from other substances in the concentrate like base materials and impurities. The molten mix forms layers by density, with denser gold settling at the bottom. The lighter impurities, called slag, rise to the top. Workers gather this slag and check it to ensure it contains no gold. If any gold is detected, the slag is returned to the furnace to remove all gold content. Once the gold has collected at the bottom of the furnace, it is extracted by tilting or pouring out the molten mixture. The gold is then poured into molds, forming doré bars or bullion. Notably, the doré bars or bullion are only about 80% pure after this process. To reach the international gold purity standard of 99.9%, further refinement is necessary. After refining, the gold is assayed to determine its purity and quality. This is typically done in specialized labs through various techniques like fire assay, atomic absorption spectroscopy, or mass spectroscopy. The refined gold is then crafted into different forms suited to its final uses, whether as bars, coins, jewelry, or other industrial products. Following environmental regulations and guidelines is essential in cyanidation processes because the chemicals used pose significant environmental dangers if mishandled. Quality control measures are put in place to ensure adherence to these environmental standards, thus preventing the release of excessive cyanide or other harmful contaminants into nature. Effective treatment of effluents and proper waste management strategies are critical to reducing the environmental footprint of cyanidation operations. These practices help safeguard the environment while allowing for the extraction of valuable resources. If you enjoyed our today's video, subscribe to our channel Factorify for more interesting videos on how other households are made.